the magnetic flux in a coil having 200 turns changes at the time rate of 0.08 Weber per second. The induced EMF in the coil is dash. Option A, 1.6 volts. Option B, 16.0 volts. Option C, 25.0 volts. And option D, 250 volts. This is actually talking about a transformer. So if we want to answer this question, the first thing we need to do is to create a picture, or rather illustrate a picture, a diagram of a transformer with these specifications, okay? So let's see if we have this as a schematic representation of a transformer, all right? And we have this, it's a turns, magnetic flux in a coil having 200 turns, all right? Changes at this. If we have this primary coil of a transformer in this form, all right? Okay, and we have the secondary coil of a transformer in this form. There is a magnetic flux around this coil, okay? That's what we're trying to say. Around this, induced by these currents. So if the magnetic flux is given as 0.08 Weber per second, the time rate is this. And the number of turns here, it could be here, it could be there. The number of turns N is equal to 200 turns. Okay? The question is, what is the induced EMF? So if this is the supply mains EP, primary voltage, this should be the induced current voltage, which is EX, all right? But that is not even what we are trying to say. Suppose we have this connected to an AC circuit with this specification, E is equal to E naught sine omega t. Good. So the induced EMF is E naught. Okay? In this whole section. So what we need to do is very simple. We can say E is equals to N d theta dt. This is the time rate of the magnetic flux. The time rate of the magnetic flux is this. And that means if we have this, we can say E is equal to number of turns given, okay, which is N theta and dt, and we call this 1. The next thing we need to do is substitute. Okay, is equals to N naught and then sine t. Where we have E, we have N the theta over the t is equals to E naught, the peak value voltage, and then omega this. But we may not need all this. We may not need all this. We don't need this. So we want to calculate this. And with that, we can simply say that E is equals to N the theta and over the t. That's the time rate. So where we have N, our N here is 200. That is number of turns. Changes at the time rate of 0.08 Weber per second, which is the SI unit of magnetic flux. So we now have 200 times time rate of the magnetic flux is given as 0.08 Weber per second. That's this. So we now have 0.08. In the actual sense, we can solve this without using a calculator. And what we need to do is just to convert the decimal points to a fraction. And here we still maintain our E because that's the one we are looking for, the induced EMF. All right? So we maintain 200 times over this, it becomes 8 all over 100. Good. What next? We cancel out wisely. 0, 0, and 0, 0 out. 2 times 8 is definitely going to be 16. 16, and that is 16 volts. So if we check very well, we have 16 volts. 16 volts, that's E. The induced EMF is 16 volts. Now let's go back to the options given. Option A is 1.6 volts, not it. Option B is 16.0 volts. Definitely, option B is the correct option, right? And that's the correct answer. Option C is not anywhere close to it or very far away from it. Option D, the same thing. So we finally conclude that the induced EMF of this is just 16 volts. That is what it should be. But if you think otherwise, comment it in the comment box. Let's discuss it further from there. I am signing out at this moment. See you.